right, class, this is Mr. Watlington. Welcome back. This is week 1. Welcome to workshop 1. What I want to just do, this is just a tutorial of some things to talk about within our workshop 1 of CIT 227, hardware and software troubleshooting. All right, let's take a look at what we got. Really going to get into, again, computer concepts. In week 1, we're talking about hardware and operating systems, and we're going to just kind of walk through some of these things for you. So actually, we talked about this, I think, in our intro, right? Our agenda with our workshop, within workshop 1, these are some of the outcomes of workshop 1, and we're just going to go through some of these things. So when we think about computing, right, a basic computer, let's talk about that basic computer. It really has, there's 4 basic processes that exist with your basic computer. What are we talking about? There's an input, processing, output, storage. So really any type of computing system, not really trying to get hung up on any specific system. We were talking about a Windows or Mac OS or whatever, but these are basic processes. The computer inside of your Roku device does this same thing, or the computer that's inside of your smart TV, does the same thing. There's the input, and your input is some type of tactical input, whether it's a keyboard, mouse. It could be a webcam, it could be a remote. All of these things can be considered an input. When we talk about processing, now this is the meat of your computing system. This is we call it the CPU, your central processing unit. Now that's where the math takes place. That's where the mathematics. We'll talk about that a little bit more as we go. Now then output. So whatever we've processed, we wanted to go out somewhere. It's got to do something. It's been processed, so we wanted to change something on the screen. We wanted to print a document or whatever it may be. And another part of that output, after the output, is storage. Without storage, our computing processes actually runs pretty slow, or won't run at all, because we don't have anywhere to maintain and keep the programs or the data that we've processed. And in our modern computer systems, that storage can be hard drives, it could be optical media, it could be a flash drive, it could be many things. It could be the cloud. You could be storing your stuff out there. So we move from that. Now let's talk about computer design, okay? When we think about the design, how computers are designed, really we start here at this bottom layer that we call your hardware layer. That consists of, like I say, your CPU, storage, memory, and yes, they're not the same. There's a difference. We'll discuss that in a second. Your input, output ports, things like USB ports, HDMI ports, display port, all of those different things that we're able to interface with the CPU, with the central processing unit. Also your power supply. All of these are part of the hardware layer. Now on top of that hardware, what do? We install some type of operating system. That operating system could be a Windows operating system, or it could be a Mac OS if you're a Mac user. It could be Linux if you may or may not be familiar with Linux. We're going to talk a little bit about that throughout the class, not specifically in this presentation right here. But all of those different types of operating systems, they are designed to be installed and run on some type of hardware. Then on top of the operating system, this is where we have applications, okay? And these are different types of user applications. Now we also have applications here that we call our operating system applications. Things like Windows Explorer, the application that sets up your printers, all of those things that are part or resident within the operating system. Those are operating system applications. So these 3 layers really make up your basic computing design, right? And those are those layers. And on top of that, then we, as the users, you and I, we interface with that through the input-output devices. Basic computer design. But however, sounds basic. I want you to remember this, because when we start talking virtualization, we're going to come back and we're going to reference this model, and we're going to build on that model a little bit. So we talked about this thing at the hardware layer called the central processing unit. Now this central processing unit, what it does it really, like I say, it's just math. It does a lot of arithmetic or arithmetic logic functions. And if you've never been familiar with this thing we call Boolean math, like kind of the and, or, nor, if, then, those types of things. But it does those types of things. Now, within this environment, really, your CPU is doing 4 basic functions. It's doing a fetch, and what fetch is, that's here on, that CPU that's on this motherboard. It goes to your hard drive to fetch programs from your computer's memory. Okay, it brings that data, that instruction from your hard drive, and it puts it into like RAM. Okay, and then once it does that, now that it takes it and it decodes, and that decoding step, that's where the program. Let's say if you're running Microsoft Word. Okay, Microsoft Word is instruction. It's software that is a set of instruction or computer code that will carry out some type of function that helps you write a document, right? Well, that decode function, that's what's happening there. It's figuring out what the program is telling the computer to do. This is what I want you to do. Now, once it figures that out, and let's say you're writing a document and you do all the things to write that document, that's takes place in that execute. That's where the requested action actually takes place. So we fetched it from memory, we've put it into registers, and moved it up into that processing unit, and now it does the decode, and then it does execute. Now, once this thing has been executed, once those lines of code have been executed, then it wants to store that. That's where it writes the answer back out of the CPU and writes it to registers or to memory. Okay, so that is really what's going on inside of that CPU, because actually, if you look at the CPU, there's 2 sections to it, right? You have the memory section where things are either being fetched from or stored to. You have a control unit, that's what does that decoding, and then this ALU, which your arithmetic logic unit. This is, like I said, this is where the fun stuff happens. This is where the Kool-Aid is actually made, right there within that ALU. Now, the thing you have to remember, really what's going on here is just ones and zeros, right? So we're just doing some type of binary mathematics, either binary addition, and it's doing a lot of comparisons of lines of code and putting those outputs out. Now, when we talk about memory, right, a big part of this is memory. So when we're talking about memory, some things you got to remember, different types of memory. You may hear these terms and may not have really grasped the difference or understanding. So we have registers, we have cache, and we have what we call just regular memory. Now, what a register, what those are, even though it's like memory, but it's sitting right there next to the CPU, and that holds the data that the CPU is currently processing. So like I said, those registers really are really a part of that whole CPU chip package set. Now, we also have cache. Now, what cache memory is, it's memory that's many times not sitting on the CPU, but it's very close and it's very fast, because that CPU is operating really, really, really fast. In the gigabit range. 3.2 gigahertz per second. So it is very fast. So what we have now, we have memory that's sitting there that also is able to give information to that CPU at a speed much faster than memory that's farther away. Kind of the thing to remember. The closer your memory is to the CPU, the faster it is. But usually the smaller it is. The farther away it gets slower, but the size gets larger. So here's what I mean. So if you think about RAM, RAM is you can have up to 6428 gig of RAM, but the speed of your regular RAM compared to this cache or these registers is very slow. However, now we talk about cache, it could be a level 1, level 2, or level 3 cache. It's operating really fast, but the size sometimes still in the megabytes. We have some caches in gigahertz speed. in size, but it's still pretty small. So that's really kind of just an overview of how that CPU works. Now let's talk about storage, okay? And this is not memory. Like I said, there's a fundamental difference between storage and memory. When we think of storage, we're thinking of things like hard drives, flash memory, your SSDs. Okay, that is storage. You know, things that are, you know, for long-term storage. And usually this type of storage is what we call non-volatile. Non-volatile memory means that after the power is shut off, whatever is in this memory is still there. That's why you could have your power turned completely off to your computer, but what is on that hard drive is still there, or what is in your SSD is still within that SSD, solid state drive. So that's what we're talking about with storage. Storage, again, much larger, much larger. Now we're talking, you know, terabytes of storage capability. The important thing to remember, though, with storage, okay? This is where your data is kept. So when we talk about security and securing a system, we always want to know, be able to secure these storage devices. This is why we use things like BitLocker, so we can do full disk encryption. So everything that's sitting on this hard drive is full disk encrypted. So in the event that someone does come and actually gain access to your data, it is already encrypted. Now, memory, not storage, memory. Yeah, again, fundamental difference between memory, storage. Different types of memory, and we call this type of memory random access, RAM, random access memory. And a lot of what we use today is called dynamic random access memory. And that's a memory chip that has to be refreshed periodically or it loses data. Now, when we talk this type of memory, we're talking about volatile memory. This means that when I turn the power off, everything that's stored in these chipsets is gone. Volatile memory as opposed to the storage side, which was non-volatile. Different types of RAM. Well, you got synchronous DRAM, which is, it synchronizes with your computer clock. So that means that it's running the same speed as your computer clock. Then we have DDR SRAM, which is double data rate SRAM. What that means, not to get too overly technical, in a sense, this is actually running twice as fast as your computer clock. What it means is that when you look at how data is written into this memory, it's written every clock cycle. So with SDRAM, every clock cycle, it takes one clock cycle to write something into memory, and then it takes another clock cycle to bring something out of memory. So that's 2 clock cycles of that computer, that CPU, to write in and to take something out. Your double data rate SDRAM, it can do both of those functions on a single clock cycle. So it can write to that memory and it can read from that memory. It can send and receive data within one clock cycle. So in a sense, it runs just a little bit faster, So let's talk about operating systems. Okay, we've talked about hardware. We've talked about the memory, different components of hardware. Now let's look at this thing we call the operating system. So when we think about an operating system, at the very heart, at the very core of this operating system is the thing we call a kernel. Now what this kernel is, this is what actually manages everything within that operating system. It talks to your hard drive. That's what actually goes to your hard drive and knows where information is on the hard drive, grabs it, brings it back, does other things with it. Really, this is the heart, which is why it's called, I guess, the kernel. This is the heart of your operating system. It does. It manages everything else. Now, on the outside of that, we have another layer that's called our application program interfaces, or APIs, and device drivers. This is what allows other things to be able to talk to the kernel, the upper layers of your operating system, to be able to interface with the kernel. And then on the outside layer of this operating system, this is where we have things, what we call our operating system file applications. And when we talk about operating system applications, please don't confuse these with user applications. There's a fundamental difference between an operating system application, like for instance, control panel. You know, your control panel is actually an application. So, think of an operating system application that is if you had gone and bought a brand new computer and the only thing that's loaded on it is Windows 10. Okay, not talking about Adobe or Microsoft Office, but all you have is Windows 10. Those functions that you can get to through Windows 10, like say, your control panel, the file manager, Windows Explorer, those is what we talk about, and these are operating system applications. Now, within this, we also have a command line or a shell, which is also what we call our command line interface. Now, if you've ever seen this, especially if you've worked in the environment with Linux or even with Windows PowerShell, you've seen this look and feel, this kind of a screen. This allows us as a user to talk directly to this to this layer, to this second layer. We're not talking directly to the kernel, but now this is a language that allows us to go in directly. And it's a very efficient way. Anybody who does a lot of work with computers, this is the way you want to operate, because it allows you to interface directly with that operating system and not have to go through a whole lot of GUI graphical user interfaces to get there. So that is what an operating system looks like. When someone says an operating system, this is what we're talking about. Now, this right here is not a part of your operating system. These are our user applications. Whether it's like say Microsoft Office or all your games and all those things, those are user applications. Not to be confused with those three layers that make up your operating system. So now that we got the hardware, we've talked about the operating system. We touched on input-output devices, mouse, keyboards, webcams, whatever that may be. Now, let's bring all these pieces together and see how it all works together, okay? So like I said, we're going to start here at the bottom with at the hardware layer. That includes our CPU, our cache memory, whether it's level 1, level 2, as well as our memory, our RAM, and hard drive, okay? That's our hardware layer. Then on top of that, we have this operating system that we just talked about, right? Yeah, so we got hardware, we got an operating system sitting on top of that, and now over here, we have our I/O devices, our input-output devices, whether it's keyboards, a mouse, printer, whatever it may be. This is how we're able, via the operating system, to talk to that hardware. So how do these pieces work together? Like I say, it starts really with the kernel. The kernel is what does the read and writes to and from the hard drive. So that kernel is what's actually going to that hard drive, getting instructions. Like I said, if you wanted to open up a Word document, well, it's going to go get instructions because you got Microsoft Word loaded on your computer, which means it's resonant to that hard drive. It's going to pull that off your storage, and it's going to write it into your main memory, okay? Now, the thing is, that's why it's so important, guys, to have as much memory in your computer as your wallet can stand. As much as your wallet can stand. Because if you start running out of memory, then everything is going to start slowing down. Everything's going to start slowing down. So now once that's written into memory, now that kernel, what it also does is its operating system, it starts to funnel that into your cache. And then from the cache into the CPU where it's processed. Okay, and that takes it through those 4 steps we just talked about: fetch, decode, execute, store, fetch, decode, execute, store, and that process happens over and over within those registers, because those lines of code are moved into the registers. Is fetch, put into a register, decode pulls it out of the register, executes, and does a compare and then sends it back out. And then after that process has been executed, like I say, that kernel is still adjudicating that process. Let's say you finished writing your document and you want to save it. Well, that goes back to the kernel, and that kernel is going to write that saved document back into your hard drive. So this is how all these pieces kind of work together. Now, when we talk about these things, even though this is a A+ class, meaning hardware, you always want to think how to operate securely. And there's some, cybersecurity implications, to how we do business like this. Now, the thing a term you may hear in this class called the trusted computing base or reference monitor. Within this operating system, whether it's all your modern operating systems, the Windows OSs and the Mac OSs, they have security measures built into here, whether it's in the BIOS, where you have to sometimes you can password protect the BIOS. There's many other security features. There's antivirus they're putting in here so we can do antivirus scans when we first turn that computer on to be sure that we're operating successfully. Also, what it also does is that every one of these processes that we just talked about, where it's doing these things called processes, it assigns a number or a PID, a process identifier, so that now as cybersecurity, we can go back and audit. Because now I can go back, I have a history of every process or process ID that would have happened. So now if I want to go back and rebuild an activity, okay, why did this individual do this? It's available because these IDs, these PIDs, they're all captured in an audit log in an event viewer. There's for instance, like in Windows has this tool called an event viewer where you are able to actually look at all these different PIDs and events from a cybersecurity perspective. All right, so actually now we've brought all these pieces together: our hardware layer, operating system, I/O devices, and how we secure it. All right, so let's wrap this up. Like I say, so in summary, like I said, we've talked about a lot of things. Like I said, we talked about the hardware, CPU, memory, storage, and then we looked at how it all works together. So that's just an overview of week 1, and we're really going and the different labs that you have in the Cengage LMS. That's going to take you through some more activities and drill you down a little bit deeper in these areas. Just want to give you an overview though of how this thing we call a computer all fits together. All right, thank you, and I hope this helps you out. Have questions, always contact me. Take care.